Okay, General Chemistry 2 class. All right, here we go. This is Dr. Oli. It is Monday, the 22nd of February. We are starting the fourth week of classes. Last week, Thursday and Friday, we had exams. And what I'm going to do today is talk just a little bit about the exam results. And then we'll move on, go through the material. Okay, this is the histogram. I'm combining the data for both lectures, so these numbers include approximately 60 students. So of the 60, let's say I think 56, 57 students. So 57 students, let's say, we had 11 people that scored 90 or above. And by the way, these are the raw scores. We had a good chunk in the B range, a good chunk in the C range, and we have kind of a significant population down here. Excuse me. So this is a little bit concerning to me that we had 13 people score below 60. However, here's something that I'm going to be doing, and I've just decided on this this morning. I'm recording this at around 11:45 on Monday. So one thing I just decided this morning is that for this particular exam, and probably for the future ones, I know it's different when you're taking the exam totally online. Same material. Sometimes the questions are framed a little bit differently. What I did was I went through the exam and I adjusted the scoring. So there were a couple of people that rose by 2 points. Some people rose by 4 or even 5 points from the original exam. I adjusted the scoring on, I think, 5 or 6 problems. And by adjusting the scoring, I mean that I actually gave more credit to certain wrong answers for multiple choice, for example. But the exam average was still fairly low. It was around a 75, which again is not a terrible average, but it's not a great one. So in the past, my average for this first exam, so having taught this for a number of years, my exam one average is typically around 80%, 80 to 81%. So what I've been doing is I'm applying a process called the normalization. I am normalizing the data to past exam averages and standard deviations. So this exam average was 75 plus or minus 17. The big standard deviations comes from people who scored down in this area. So what I'm doing is by applying the normalization, it shifts the average up a little bit. And so some people down here will gain some significant points, perhaps 8 or 9. People at the top end may gain 1 or 2. The process does is it will actually compress some of these scores, moving the exam average higher, and it'll tighten up the standard deviation a bit. So I will explain more. The exam data that are shown right now for your Moodle scores, those are the raw numbers here. I will add eventually another column that will show exam one data normalized. And so the normalized data will be the exam average that I currently have in my spreadsheet for your score for this. Okay, so for the announcements. The most important thing right now is to get on ALEKS chapter 20. We've already talked about a couple of concepts, at least in this class and the online class. After today, I'm going to try to be better synchronous with both of my lectures. So in fact, I may even be recording my Gen Chem 2 lecture in class and then posting that. So ALEKS chapter 20 is due tomorrow night. There are only 3 objectives. Only 3 objectives. And we'll go through everything you need to know today. After chapter 20, we're doing chapter 15, which is thermodynamics. That's going to be due on Friday. We're taking 2 days on thermodynamics. That's Wednesday and Friday. At least that's the plan. If we need more time than Friday, then I'll push back the ALEKS due date for chapter 15. Notice that there is only one ALEKS assignment for all of chapter 15. The goal then is, if this is due Friday night, then you'll have Saturday and Sunday for Open Pi. So you can go back and work on anything else, get caught up, and then you should be okay. Don't forget the nuclear chemistry lab this week. Make sure that you've got your Excel calculations completed for your write-up for tomorrow and for Thursday for lab. And then there will be a quiz on Wednesday. It'll be like a short 7-minute quiz, and it will be over the same things from that we'll have talked about from the exam that we had last week. Same topics, some of the exact same questions we'll revisit. And then finally, just putting it on the calendar, exam 2 is coming up in a couple weeks. So whatever material we cover between now and March 8 will be on the exam March 9 and 10. How are we doing with that? Any questions? No questions? All right, I think we're good then. So just so you know, I don't do despair when days after the exam. So we're going to continue in chapter 20, nuclear chemistry. These are the 4 particles related to nuclear chemistry. There are a number of particles that they'll talk about in the book, in the manual, in ALEKS, and in the text. So the alpha particle, remember, it's a chunk that contains 2 protons and 2 neutrons. So the nucleus, remember, we don't even worry about the electrons now. They're totally separate. They don't matter for nuclear chemistry. It's just the nucleus, the protons and the neutrons that are held together. An alpha particle, 2 protons, 2 neutrons, that chunk is a helium nucleus. That's why we call it, it has a mass of 4 and a charge of +2 because it's 2 protons. That is alpha. Beta, a nuclear electron. It is when a neutron turns into a proton and it kicks out an electron as a result. We can't have electrons in the nucleus. Even though the electron comes from the nucleus, that's a beta particle. Gamma rays are only radiation, very, very high energy radiation. And then the positron is a particle that is just like the nuclear electron, but it has the opposite charge. Same mass of an electron, +1 charge. Now, I think I talked about this in the last video. So to quickly review, how do we balance nuclear reactions? Well, in the case of, here are examples where alpha particles are being produced. Here is an example where beta particles are being produced. In other words, this is a product. This could easily be written alpha. This could easily be written beta. Notice that we didn't even put the charge here. We didn't put the charge here because now with nuclear chemistry, the only time charge doesn't matter. Same thing here. We don't have the charge on the electron. The charge is indicated down here. And then the charge on the alpha particle is indicated here. So in balancing nuclear reactions, the atomic number on the left has to equal the total atomic number on the right. 92 is equal to 2 plus 90. And the mass on the left must equal the total mass on the right. 238 is equal to 4 plus 234.
Unknown caller.
And I'm going to, sorry about that. Yeah, of course, of all things. Okay. Yeah, right while I'm doing the video, I get a call. No one ever calls me. All right. So here are some other types of radioactive decay. What I would expect you to do is if I were to give you a reaction like this, okay, except for gamma radiation, you can't predict that. For example, since the numbers are 0, 0, there's no way you could know if you have 0, 1, 2, 3, or a dozen of these. Aside from this guy, if I were to give you a reaction like this with 2 of the 3, you should be able to find the third, balancing nuclear reactions. So here's an example of just producing gamma rays. Here's an example of producing a positron. Notice here that this is an electron with a +1. So here's an example of positron. You typically have positron emission when you have smaller nuclei that are not stable, undergoing some kind of a nuclear transformation. And then here is electron capture. Notice all it is instead of a beta particle being a product, a beta particle is a reactant. That means that this big nucleus is absorbing this electron and it converts into something else. These are reactions that I believe I showed you before on the video. Okay, I'm not going to take time to balance nuclear reactions, but practice. The worksheet 8 is now up on Moodle. That assignment is due Wednesday night. So even though Alex is due Tuesday night, tomorrow night, the worksheet is due Wednesday night. Worksheet 8. Make sure that you catch that assignment on Moodle. All right, so here we have complete the reactions. Again, I think I did a couple of these, but I don't remember. I never remember what I've already done. So what I'm going to do now is let's just finish off a couple of these. Here's platinum 170. And of course, I forgot my periodic table. Yep, of course I forgot my periodic table. And we don't have one in the lab. So platinum, what's the atomic number of platinum? All right, I guess I'm going to have to look up on Moodle. Sorry about this, you can just speed through this. On the video, here we go. Platinum has an atomic number of 78. So platinum is 78. And let's go back to this. Here we go. Okay, platinum is 78. So we have 170 platinum instead of 78. I hope so. My short-term memory loss. Okay, that's what happens when we get old. 166 OS. And of course, I didn't look up OS. So let's see what that is. Osmium is 76. 76. How do we balance this? Well, we know our mass on the left, we know our mass on the right, we know that it's something more. 170 is equal to 166 plus 4. 78 is equal to 76 plus 2. This is clearly an alpha particle. That's it. That's all there is to balancing them. Now, what if we had, just saying, what if we had something like this, where we have 170, 78. By the way, you notice how from the element, I just looked up the atomic number in the periodic table. If it's atomic number 78, that's platinum. If it's platinum, it's atomic number 78. These define each other, 76 for osmium. So what if instead on the right, we had 162 and 72? Well, I could look up whatever that element is, 72. Yeah, and it's not coming to me right off the bat. Then the difference would be 8 and 4. Well, if I have something like 8 and 4, that's 2 alpha particles. So that would simply be something like this. Okay, so you see how easy this is? Hopefully it's easy. So up here, we have thorium and protactinium. They have the same mass, guessing there's going to be a beta particle involved because it has a mass of 0 and a charge of -1. If this is radium giving off helium, what's the difference? So obviously with the electron, this is going to be -1. Unless you're told it's a positron, this will always be -1. Unless you're told this is a positron, this will be -1. Okay, a radioactive decay series. We're going to look at these. Basically what we have with the radioactive decay series is that we have something starting here, look up the atomic number. It is producing an alpha particle, number here is 2. So you simply find what this thing is. This is the product of the decomposition of thorium. This number then goes down here. And this thing loses a beta particle to produce something else. So keep in mind, the mass will not change, but the charge will increase by 1. This thing then becomes the reactant for the third step. This is called a radioactive decay series. This is what happens when you have these very, very heavy elements at the bottom of the periodic table. And in most periodic tables, you see that some of them are shaded or they're outlined. And that's an indicator that there is no known stable isotope of those elements. They're all radioactive. In other words, they have unstable nuclei and they undergo these reactions until they reach an isotope that's stable. They'll kick off alpha particles, they'll kick off beta particles. Here is a different radioactive decay series. How do we find what this is? Just like balance any ordinary nuclear reaction. The masses here, it's going to have a mass of 238. PA is, yeah, I don't remember what it is, but whatever that is, it's going to be big, like 90s. This plus 2 is going to be the atomic mass of that thing. So the 234 PA is our reactant for this step. The product that we get here is the reactant for the third step. It's a way that these very heavy elements, these huge nuclei, reorganize to try to become more stable. Now, there are several radioactive decay series that are known. In almost all of them, the most stable byproduct that's non-radioactive is lead. It's an isotope of lead. So this is one reason why there's so much lead around. I mean, lead is available, you find it in the environment, and it's cheap, it's abundant. It's also fairly toxic for a number of things, but lead is pretty ubiquitous because of the fact that these elements over the millennia, centuries, billions of years, have ultimately settled down, they have decayed into the stable isotope of lead. First order kinetics. So here's pretty close to the end here. Here we have a radioactivity problem. And so the one thing to know, whenever we've got a nuclear reaction, it is one nucleus undergoing a reorganization. All nuclear reactions follow first order kinetics. Did you get that? All nuclear reactions follow first order kinetics. So here is what we have. The radioactive decay of thallium-206 to lead-206 has a half-life of 4.2 minutes. But we have this many atoms of thallium. Determine the number of thallium atoms left after 42 minutes. So we just used all we do here is follow first order kinetics. We know that natural log of, in this case, what I'm going to say is the number of atoms at time t over the number of atoms at time 0. We could use concentration, but we don't have concentration. We have numbers of atoms. So it's this ratio is equal to minus kT. We also know that, and this is the first order integrated rate law. We also know that the half-life is this for a first order reaction. All right. Has a half-life of 4.20 minutes. So if we know the half-life, we can find K. So I'm going to do that right here. I hope this is on the screen. .693. Rearranging this equation to solve for K. Jeez. 4.20 minutes. So K has a value of 0.165 minutes to minus 1. That K is the same thing as this value here. Here we're given the time, so we know K. Now for the big problem, we know K because we just calculated it from half-life. We know the time, which is 42 minutes, and we know the starting number of atoms. The question is determine the number of atoms left. So we're looking for n sub t. So natural log of n sub t, I'm just going to leave this as n sub 0 for now, is equal to minus 0.165 times, let's see, 42.0 minutes. Time and K. So if we multiply this out, 6.93. If we hit e to the x, 1022. So n sub t over n sub 0 is equal to 1000. Oops, I forgot to change it. So boy. See, this is what happens when you don't use the negative sign. Let's see, so this is change sign. 6. That is e to the x. That is 9.78 times 10 to the minus 4th. 9.78 times 10 to the minus 4th. A unitless ratio. So now the number of atoms, n sub 0, is this, 5 times 10 to the 22. So n sub t is equal to this times n sub 0. Times 5.00. That's atoms. And we get 4.89 times 10 to the 19th. First order kinetics. So we use the integrated first order rate law. This is how many atoms we have left after 42 minutes. Okay, I hope that's straightforward. This is just like what we did in kinetics. This is also why we follow chapter 14 with chapter 20. We'll touch on just a couple of more topics here. We're not going to have you do any calculations with nuclear binding energy. I'm not going to have you do any in ALEKS. So I deleted that section. But here's what I want you to know. I want you to know how it works. So here's what happens in a nucleus. Protons and neutrons. Those protons don't want to be together. They're +1 charged and they're jammed together. And we know that like charges repel. So what holds the protons together in the nucleus? Notice we have lots of neutrons in there. What's the glue that holds them together? The glue that holds them together is called nuclear binding energy. So let's take carbon-12. Carbon-12 has 6 protons and 6 neutrons. Carbon is atomic number 6, 6 protons, 6 neutrons for carbon-12. If we know exactly the mass of a neutron, we know exactly the mass of a proton. These have been determined experimentally and they're known for a long time. So if we take 6 individual protons and 6 individual neutrons, and we add their masses together, we should get the mass of the carbon-12 nucleus, right? Sum of the parts is equal to the whole. But the answer is, no, that's not the case. Carbon-12 weighs less than the sum of its parts. It weighs less than, the nucleus C12 of C12 weighs less than the mass of 6 protons plus 6 neutrons. The difference in that mass is called binding energy. That's binding energy, and it's calculated from Einstein's famous equation, E equals mc squared. The mass difference is converted into the energy that it takes to hold the nucleus together. Nuclear binding energy. So here's an example. No, guess we're not there yet. So here's how you go through a nuclear binding energy problem. You add the mass of protons and neutrons individually. Find out, you know the mass of a proton, you know the mass of a neutron, those are given. Subtract the mass of the nucleus. That's the difference in the mass between the sum of the parts and the whole. Then we have a mass in atomic mass units. Convert that mass to kilograms. From that mass difference, we calculate the energy that holds it together. C is the speed of light. So here's the example. The atomic mass of a proton is 1.007825. For a neutron, 1.008665. Notice that these are close, but not the same. The difference is about the mass of an electron. So we have here's carbon 13 instead of carbon 12. 6 protons, multiply this by 7 neutrons. So we get the mass combined for what the carbon 13 nucleus should be. Sum of the parts. The mass of the 13 atom can be measured exactly, precisely with the mass spectrometer. The mass of the carbon 13 atom is actually this. It is less than the mass of the parts, mass of the sum of the parts. The difference in mass is 0.1 atomic mass units. An atomic mass unit is connected to grams by Avogadro's number, 6.022 times 10 to the 23rd. So we take AMU and convert to grams by dimensional analysis with this relationship. So the change in mass, if we convert this not just to grams, but also to kilograms, another factor of 3. So this is on the order of 10 to the minus 25th grams, 10 to the minus 28th kilograms. Now, the speed of light, 2.997925 times 10 to the 8th meters per second. The speed of light, we square that, this number, times that gives us the change in energy, 1.6 times 10 to the minus 11th joules. This is the energy to hold the nucleus of one carbon atom together. Just one carbon 13, just one carbon 13 atom. That's the energy for one atom. Okay, let me back up. So if we want to convert this to moles, so this is joules per atom. If we convert this to moles, we would multiply this by 6.022 times 10 to the 23rd atoms per mole. So multiply this by 10 to the 23rd, and now we're looking at a number on the order of 10 to the 23 minus 11. 23 minus 11, is that around 14? Something on the order of 10 to the 14th joules per mole. That's a lot of energy. 10 to the 14th joules. In most chemical reactions, we're talking about, let's say 100 kilojoules. Let's say 1,000 kilojoules. So 1,000,000, 1,000 kilojoules, which would be 1,000 kilojoules is 1,000,000 joules, 10 to the 6th joules. So if this number is on the order of 10 to the 12th joules, that's like 1,000,000 times order of magnitude than we would have for a normal chemical reaction. Okay, this band of stability. I told you in the last video how for lighter elements, you have basically a 1-to-1 proportion of neutrons to protons. As we get heavier, we need more neutrons. We need more neutrons to kind of spread those protons out. Remember, these are in 3 dimensions, and they are all jammed together. And the nuclear binding energy has to increase as you go to higher and higher masses until you reach a certain point. So what we have here, why do we have radioactive isotopes? It's because we get radioactive things that are outside of this band of stability, this ideal neutron to proton ratio. If they're out here, it's going to emit radioactive particles to get closer this way, or it will emit radioactive particles to get closer this way. So radioactive isotopes, excuse me, that are outside this band, they're moving toward where these red, these are stable isotopes. These are stable isotopes. This is mercury 202 right up in here. So once you reach a certain point, anything beyond that, those are unstable. So these gray dots, they are isotopes that exist, but they're not happy. They're trying to decay into one of these isotopes that are represented by a red dot. So binding energy per nucleon. The binding energy per nucleon is simply the total binding energy for a nucleus. So for carbon-13, we know the total binding energy. We know the total binding energy, let's say per atom. But we divide it by the number of protons and neutrons that we call nucleons. So for carbon-13, we would divide that total binding energy by 13 to get binding energy per nucleon. And that's what this graph represents. Uranium's way out here. This rises until we hit iron 56. Then we have the steep drop off. This gap here between these heavy elements, like where uranium is, and iron 56, if uranium undergoes a nuclear reaction, it will give off energy in binding energy per nucleon in this area. It's a tremendous amount of energy. This is where we get nuclear reactions. So nuclear reactions are producing tremendous amounts of energy. And so for the atomic bomb, it is fissionable uranium, this energy gap, that's what is observed when that bomb goes off. The hydrogen bomb, on the other hand, we're talking about, let's say, tritium. Down here, it's a bigger gap. The difference between tritium and helium and some of these others, lighter nuclei, that gap is much larger than the gap here. This is where we have smaller nuclei that fuse together, that combine together. And when that process happens, they give off even more energy. So this is why fusion reactions are so much higher energy than fission reactions. Fission is a large nucleus disintegrating. Fusion is where light elements, light nuclei combine. This is the beam at CERN. It straddles the border of France and Switzerland, near Geneva. This is a particle accelerator, and this is where they're doing a lot of reactions, a lot of atom smashing, where they're taking subatomic particles and ramming them into each other and seeing what happens. This is actually a picture that I took at CERN, just for scale. This is a worker down here in a hard hat. This is the Large Hadron Collider. And you can see that, and this is about 100 meters underground. So just to get a size or a sense of the scale of these experiments that are going on, it's tremendous. So they're smashing particles against each other right here in the middle. Of course, this is down for maintenance. And then all of this stuff around are detectors to look at particles that are produced in their energies. Okay, so here is a brief summary of nuclear fission. Heavy elements split once they're hit by a neutron. They produce lighter elements, and in the process of being split, they produce two lighter elements and more neutrons. Those neutrons split other uranium atoms. So it's used for nuclear power. Nuclear power plants typically use uranium-235. And weapons, how to get rid of waste. That's a major issue. So here's an example of a fission reaction. Uranium-235, it absorbs a neutron. It says, whoa there, I'm not happy. It splits into two lighter elements plus three more neutrons. Here's one of the reactions at the bottom. In a nuclear reactor, the real key is absorbing the neutrons that are produced. If you absorb the neutrons, you control the reaction. So these are control rods, carbon, cadmium, some other things that help absorb neutrons. The energy that's produced runs a boiler. And so you're producing a tremendous amount of energy. There's a downside to nuclear energy, that we see here. Nuclear fusion. significantly more energy released per nucleon. Nuclear fusion, in order to get initiated, requires a tremendous amount of power. In fact, it requires a fission reaction that produces enough energy to cause the fusion reaction to occur. In practice, it's really difficult to control this. There are several locations around the world, including Princeton in California. They have fusion reactions where they're trying to control this. Once you get fission going, it can be maintained, but it's very difficult to isolate it. The results, you get very clean products and a tremendous return on your investment as far as energy is concerned. Okay, and here's where they're trying to control the fission reaction with lasers. The fusion bomb is about 10 times, it's at least an order of magnitude more powerful than a fission bomb. All right, we are done. Make sure that you get Alex done by tomorrow night, and don't forget the worksheet that's due on Wednesday night.